Okay, hi all, welcome to this physics seminar where we have Professor Mark Alford from Washington University, St. Louis. Let me say a few words about Mark. So Mark did his bachelor in Oxford University, then he moved to Harvard for his master and PhD studies. After that, she had several postdoctoral positions, research positions at quite prestigious universities like Cornell, Kavli Institute for Theoretical Physics in California, Santa Barbara, then Princeton and MIT. Then he moved to University of Glasgow as a lecturer, and finally he received a professor position in the University of Washington, St. Louis, where among others he served also around 10 years as a department chair for the physics department. His research is quite interdisciplinary, I would say. So he's trying to combine aspects and phenomena from particle and nuclear physics, condensed matter physics, and astrophysics. And the main focus of his research is dense matter inside neutron stars, which is a topic that I guess we will hear also about today. So the title of the talk is Neutron Star Emergence as Materials Science. Thank you very much for being here today. We're very much looking forward to your presentation. The stage is yours.
Thank you. Thank you very much for the very nice introduction. So yes, it's a great pleasure to be here, to just come down the road to Rolla and meet people in your department. It's wonderful to be here. So yes, I'm going to talk about neutron star mergers as material science. This is, just to give you a sense of where I came from. Of course, St. Louis is famous for its half McDonald, and we have nice buildings, and of course, we spend a lot of time studying in the library. Okay. Let's see, this will go the way I want it to. I see. Okay, so I get partial screen. Let's see a bit of the next screen. Just try that. Here we go. Okay. Nice. All right, good. So I'm going to talk about phases of matter. So let me start off by talking about a very familiar piece of matter, which is water. And as you know, when you compress, heat up water, you get different phases. We're familiar with solid and liquid and gas. This is how it works with water. This phase diagram, maybe to some of you, it looks like it's on its side. Different people like to put the axes in different directions. So I've got pressure along here, temperature up there, and we live at 1 atmosphere pressure. We spend our lives going up and down this line. So we get to see liquid water turning into ice at 0 Celsius and liquid water turning into gas at 100. And that's how the world looks to us. But if you increase the pressure, you find that the distinction between liquid and gas water goes away. It's first order phase transition ends. If you reduce the pressure, you find the melting point rises and the boiling point goes down, and eventually they become the same temperature, and you get this famous triple point. And then below here, you go straight from ice to water vapor. So we're very familiar with phase diagrams of this kind. And what I'm going to be asking about is phase diagrams for high density forms of matter, very high temperatures, or particularly very high densities, where we're not even talking about atoms anymore. You've compressed it so much, the atoms have collapsed. And you're not talking about atoms or molecules reconfiguring themselves into different phases. You're talking about neutrons and protons, or even quarks reconfiguring themselves into different phases. And so now you're looking at these sorts of crazy temperatures. We use different units, right? We use mega electron volts per cubic femtometer Fermi. In the units that people are more familiar with, we're talking about temperatures of 10 to the 10, 10 to the 12 Kelvin, or Fahrenheit or Celsius at that point. That's really matter. Densities that are, as you can see, considerably higher. The density of water is 1,000 kilograms per cubic meter, but we're talking about stuff that's been compressed down many orders of magnitude. So, for example, a fully loaded oil tanker would be like a little grain of salt, very high density materials. So where do you get these sorts of crazies? Way up, we're not down here, we're way up, very high density. Where do you find this? Well, astrophysically, you find it in neutron stars and in how they're born in supernovas and in how some of them die in neutron star mergers. And that's mainly what I'll be talking about today. You can also recreate at least the high temperature conditions at some facilities on Earth, like in Brookhaven, exotic places like Darmstadt and places like that. So, but I'm going to be more focused on the astrophysical context for this sort of ultra-close material. Okay, so what's the analogous phase diagram? Well, here is what we know. And what we know is a little bit on the simple side. So we've got, along here, we've got this chemical potential, which is basically telling you about density. You turn the chemical potential, this is chemical potential, a baryon number, so more neutrons, more protons per cubic centimeter. So you're turning up the density along here, you're turning up the temperature up here, and we've got this little line here, the nuclear gas liquid phase transition. So below this line, you've got some sort of gas of neutrons and protons. Above this line, you've got a liquid of neutrons and protons. And you've got various places where this phase diagram is probed in nature. So you've got heavy ion collisions whacking nuclei together and making them very hot. This is your sort of 10 to the 12 Kelvin, 100 MeV temperatures up here. And we think making a quark gluon plasma. And you've got neutron stars, colder but denser out here, made of nuclear matter, just neutrons and protons wall to wall, cubic kilometers of just neutrons and protons. And then you've got neutron star mergers, which whack them together and heat it up a bit. So neutron star mergers are interesting because they're probing this sort of area of the phase diagram. But really, all we know is just this very basic part that there's this nuclear gas liquid phase transition. That's really the only thing we know. And above it, we expect some sort of nuclear liquid, which might be a superfluid or a superconductor. Where are you right now on this phase diagram? Any ideas? You must be there somewhere in the phase diagram. Matter. I mean, I'm here, very low density, very low temperature. Yeah, it seems plausible, doesn't it? But no, you're not. You're actually here because you are a mixed phase. You are a fine mist of little droplets of nuclear matter separated by vacuum. Well, there's electrons, but that's okay. So you are this mixed phase nuclei are little droplets of nuclear matter, and you are this just lots of little droplets of nuclear matter separated quite widely in space. So you are this this mixed phase of nuclear matter and vacuum. So you are here. But what we are sadly not interested in you. We are interested in what happens as you push up the high densities and maybe higher temperatures. We're interested in what's going on out here in the space diagram. Already. Here, it's like tens of MeV. Yeah, tens of mega electron volts, the 11 Kelvin. So, okay, so we have conjectures. We don't have data, but we have conjectures. So here is our conjectures are that there's some sort of quark matter phase out here that we call the color flavor lock phase. There's nuclear matter down here, and in between, who knows what, right? At low temperatures, you can get all sorts of interesting ordered phases, and we really don't know different phases in which the quarks Cooper pair in different ways, or maybe the neutrons and protons, maybe they're Cooper pairing down here, but maybe they're doing something else in here. Who knows? We really don't know. Yeah, we'd like to know. And where can we? And we think there's this chiral phase transition line ending at what they call the chiral critical point conjecture. Again, the heavy ion collisions are trying to probe for this kind of thing. And I'm going to talk more about the not so high temperature, high density part of the phase diagram, which is where neutron stars and neutron star mergers are the only instances that we know of in nature where matter of that very high density and moderate temperatures exists. So that's the place I'm going to be looking at from a theorist's point of view. Everybody, good questions? All right. So yeah, neutron stars. Who knows if they get dense enough to have quark matter in the middle? I'm not going to talk too much about quark matter. Mainly, I'm going to talk about nuclear matter and what happens to it in neutron star mergers. So let's get to that. So when you observe a neutron star merger, what do we see? Well, as you know, some of you here, this is your job, but some of you may not know so well. So we see gravitational waves, or you might say we hear gravitational waves coming through the cosmos to us from mergers of neutron stars. At least we've got maybe one or two that we've observed, and we hope to observe many more of them. And this is what happens when you have a binary system of two stars, and they both go supernova at different times, and which ends up making two neutron stars. You have a binary system of two neutron stars. They spiral around each other, emit gravitational waves, lose angular momentum, and eventually spiral in and merge. So that is how neutron star mergers happen. And so they merge, and okay, then there's a ring down, and they may collapse to a black hole. The in-spiral emits gravitational waves, the actual merger emits lots of gravitational waves, and so we hope to observe this sort of signal in gravitational waves, and ideally some sort of electromagnetic signal alongside it to do with the electromagnetic energy released when two neutron stars merge. And from an astrophysicist's point of view, this is interesting study of astrophysical objects. From my point of view, as more of a nuclear particle type physicist, this is an interesting experiment to study the properties of the dense matter that the neutron stars are made. This is how nature gives us an experiment which probes these properties. And so we like, ideally, to be able to connect the properties of the nuclear matter to what is observed in the gravitational wave signal from a merger and maybe the electromagnetic signal from the merger. So this is what we hope for. This is all theory here, like pictures and theory. And so we're going to need to understand with microscopic physics, how does the whole thing behave? And running it backwards, what do the observations tell us about how nuclear matter behaves? So this is what we actually had so far, the best merger event we have, this one, where we saw frequency as a function of time from merger. We saw this in spiral where the frequency rises, it's going around faster and faster and faster and faster and faster. We saw these gravitational waves, and then just when we got to the good part, suddenly somebody blanked the screen, and we don't see the merger itself because the signal goes behind the noise. So the detector is very frustrating. But with future detectors, we hope we will actually get the whole thing. We'll get gravitational waves from the last part of the in-spiral and the merger. So that's what we're thinking about right now. We're thinking about how we have the necessary theory of the behavior of this material, these two blobs of nuclear material. We need to understand the microscopic properties of those two blobs to feed into the simulations of the merger that will then make predictions about what we should see in terms of the signal. And then when we actually have the signal, we can run the pipeline backwards and say, what does it tell us about the properties of the material? Any question about the big picture? Okay. All right, so the outline of what we're going to do today is, well, I've already said this, we're thinking of these neutron star mergers as natural experiments to probe the properties of dense matter. And if you ever have had or have people here talking about this sort of physics, a lot of what they'll talk about will be the equation of state. The equation of state meaning, how much denser it gets when you compress it a certain amount, right? Just pressure as a function of density. So the equation of state is fine, but I'm not going to talk about that because there's enough people to talk about that. I'm going to talk about out of equilibrium phenomena, which are also important because it's a dynamic process, right? Neutron star merger, time dependence, as we'll see. So what sort of out of equilibrium phenomena might we be interested in? The main one I'm going to talk about is flavor equilibration, which is related to bulk viscosity. So I'll talk about that quite a lot. Another thing you might be interested in is thermal equilibration, temperature gradient. This part's hotter, that part's not so hot. Heat flows from one to the other, thermal conductivity would be relevant. Or shear flow equilibration. This part's going this way and that part's going that way, and there's some interaction between them that leads to shear viscosity to even out the flow. And my main point is that this is better than the equation of state for probing the phase structure. Remember, we started off talking about phase diagrams, want to know, are there different phases of dense matter? You want to distinguish different phases from each other. What do you look at? Well, think about how terrestrial dense matter works. If I want to decide if something is a superconductor or not, what do I do? Do I compress it and see how much denser it gets when I compress it a certain amount? No. It behaves pretty much the same, whether it's superconducting or not, right? A chunk of that. What I do is I stick electrodes on it, push it out of equilibrium a little bit by putting voltage across it, and watch how it responds. And so you're looking at response to being pushed out of equilibrium. That's what tells you about different phases or discriminating than the equation states. So that's one reason to be interested in these out of equilibrium phenomena. They're better at telling you what different phases are. So the thing I'm mainly going to talk about, as I said, is this flavor equilibration. I'll tell you in more detail what it is. And the sorts of things we'll end up talking about are relaxation time for the proton fraction, critical equilibration, when the relaxation is important physics, how it manifests itself, this equilibration, in things like bulk viscosity and accumulation of sound. So this part here is what we're mainly going to be talking about in the next half hour.
So are you mostly looking at linear response?
Yes, mostly at linear response.
Or is it two non-equilibrium?
Linear response is two non-equilibrium. It's just perturbative, but not equilibrium. So most of what I'll be talking about is linear response, but we can, in fact, for this particular kind of out of equilibrium thing, we can look at non-linear. We can push it on linear regime. It's still tractable. If you ask me later, I can talk about why, and it will make more sense once I've talked about the main thing, which is linear response. For any other? Okay, so what sorts of situation is the man itself in? Here is a couple of slides from a simulation showing which range of density and temperature gets probed in a neutron star. So the axes here are multiples of nuclear density. So this would be the density of a nucleus, twice the density, 3 times, 4 times, 5 times the density of a nucleus. And here is temperature in MeV. And 1 MeV is 10 to the 10 Kelvin. Okay, so that's why we use MeV. So 10, 20, 30, 40, 50 MeV temperature. And this is about 2 seconds after the neutron stars touch. And what they've done is they've taken everywhere in that, there's a terrible car accident happening, right? All sorts of craziness going on. But every point in there, they said, what's each fluid element in that maelstrom? With each fluid element, they said, what's its density, what's its temperature, plot it on here. So you get to see what range of densities and temperatures the merger is probing. So you see there's bits of nuclear matter up to 3.5 times saturation density, nuclear density. In this particular simulation, different simulations using different equations to take and be different initial masses, different properties of the merger. But roughly speaking, goes up to a few times nuclear density and temperatures varying, but going up to about 60 MeV. And then 10 seconds after the merger, it's settled down a little bit, but it's still, now it's exploring up further. The whole thing has sort of settled down a bit and crunched down under its own gravity, probing up to higher densities, and its temperature is about 40 MeV. And so the colors on this are a bit incomplete. I think the red is not coming through well. But these blue parts here are near the middle, and these yellow parts are at the edge. So red. But so the middle is denser and not so hot. The edge is not dense and not so hot. And actually, the sort of middle range of radii is where it's hottest. But the main point of this slide is just to say that it's a very non-uniform process. As you expect, slamming two things into each other, you've got variations in temperature from place to place, variations in fluid flow because it's varying in time, variations in density over time, which, as we'll see, leads to this flavor re-equilibration.
And is that the color one for the
Sorry?
Like the color map.
So the color map in this case is representing how far, radius in kilometers from the middle. Okay. So the message here is just that it's a very non-uniform process and plenty of room to study stuff that's out of equilibrium. Spatial gradients, temporal variation, plenty of room for things to be pushed out of equilibrium.
It's really far away from the linear transmission, right?
Probably, yes. Yes, right. Yeah. And the time scale, just to bear that in mind, the time scale that we're looking at is in the sort of milliseconds, tens of milliseconds. That's the time scale. How long does it take these things to go from two separate things to basically one roughly spherical blob? 10, 20 milliseconds. That's the time scale. And these things are the size of a city, right? They're 20, 30 kilometers across. So stuff's happening, a lot of stuff. So I'm focusing on density oscillation, okay? Density variation in time. So this is where they do some tracers. So we select some little fluid elements in the situation and we track them through time. So these portable fluid elements innocently sitting in the middle of a neutron star, thinking it's got a peaceful life for the next 100 million years. And then suddenly its neutron star crashes into another neutron star and it finds itself riding this crazy stormy sea. And it undergoes wild density oscillations according to this simulation. So you see, it starts off at twice. These are a bunch of different fluid elements, different lines. Yeah, but they start off something around twice saturation density, and then they suddenly get uncompressed to more like saturation density, and then compressed to 3 times, and then uncompressed, and then compressed, and then dragged around the place, squeezed, unsqueezed, squeezed, unsqueezed. All sorts of terrible things are happening with this fluid element in the first 10 milliseconds or so, and then it settles down. It's just being sort of vibrated, not vibrated, sort of rhythmically squeezed. Sort of jumped on, but for a few tens of milliseconds, and then the simulation ends that. So the main message here is that the fluid elements are experiencing dramatic density oscillations, particularly in the first few milliseconds. The amplitude can be up to 50%, certainly the nonlinear regime gets a bit more linear later. And what sort of frequencies are we looking at? We're looking at sort of kilohertz frequencies, right? It's about 1 millisecond or so for the oscillation period. So the sorts of out of equilibrium conditions that we're looking at are density oscillations with frequencies in the kilohertz range and amplitudes that could be quite large. So we want to know how is the material going to respond to those conditions.
And everybody, well, these fluctuating behavior that I see at long evolution time, is the kind of thermalization.
It's not that it's equilibration. It's thermalization is in there somewhere, but this is the whole 2 neutron stars have become 1, and it's still sort of ringing, right? It's ringing down. Okay, so it's settling down in every way, like thermal and there's probably shear viscosity evening out the flows. There's thermal conduction evening out the temperature gradients. There's also but what I'm going to focus on is a particular aspect which is flavor equilibrium, okay, which I'll explain in a second.
Does it mean also that temperature increases as time evolves?
Not necessarily, no. The temperature in these simulations, the heat comes from shocks, and they don't have thermal. The simulations don't have thermal conduction. So actually, as they are now, the simulations are not well placed to answer questions about thermal equilibration.
Is the field controlled by the Christmas state?
In a sense, yes, but the period of oscillations in neutron stars all tend to be in the sort of kilohertz, maybe tens of kilohertz range, because all the equations of state tend to have a speed of sound that is in the kind of some fraction of the speed of light range, 10% of the speed of light or something. And if you just ask how long does it take to go from one side to the other at a tenth of the speed of light, it takes about a millisecond. So yes, it comes from the equation of state, but not in a way that would allow you to distinguish one equation of state from another. It's very check. Did that? Okay. Okay. All right. Okay. So let's start talking about the fluid, right? I've been talking about this material, this fluid. So what is this nuclear matter fluid? What does it consist of? Well, the simplest hypothesis is it's just regular nuclear matter, which means it contains neutrons, lots of blobs here, protons, there's a smaller fraction of protons. Electrons, equal numbers of protons and maintain electrical neutrality. And neutrinos, which may or may not be thermally equilibrated. It's not, but they're the complicating factor. I drew them in these sort of arrows. So it's basically a neutron proton electron fluid with some neutrinos. And so you describe it by some. So how do you describe a fluid element? What do you need to tell me? What do I need to tell you so you know what the state of the fluid element? Well, I can give you the baryon density, the neutron plus proton density, how many baryons per cubic Fermi. I give you the temperature, and I give you the proton fraction. These two together are a way of telling you separately the neutron density and the proton density, right? The total baryon density and the proton fraction. And then maybe if neutrinos are trapped, you are interested in the electron fraction. I really won't be talking about that today. I'll mostly be imagining the neutrinos escape. So pretty much, I only need to know three things. Fluid element is described by baryon density, temperature, and proton fraction. Then I know what I need to know about the fluid. Yeah.
Actually, in this context, how do you define some of the definition that define specifically what definition? You have to have some mechanisms of suiting energy and information fluid elements, which are timescales much shorter than the.
Well, that's what we have. Strong interaction, right? Neutrons and protons interact by strong interaction. Electrons interact by electromagnetism. The characteristic timescale for the strong interaction is 10 to the minus 23 seconds. The characteristic timescale for electromagnetism is maybe a bit longer than that because it's 100 times weaker or something. So maybe 10 to the minus 20 seconds. And the timescale we're interested in is 10 milliseconds, right? So we are very well, we have a lot of time to be thermally equilibrated, except the neutrinos, right? Which are weakly interactive. That's why I don't want to talk about them.
And those can basically have a mesh size.
Well, the mesh sizes are typically 10 to 100 meters. Okay, but I'm talking about a fluid element. I'm doing microscopic physics, which I will then give to the merger simulation people to use to say how their fluid elements should behave. Right, so I'm not trying to do a merger simulation. I'm trying to do the microscopic properties of the material, which will then be incorporated input into a merger simulation. Does that make sense? Okay, so it's thermalized. Right, the neutrons, protons, and electrons are thermalized. They've had many times enough time to share energy equally among all the three because they're strong and electromagnetic interacting.
Charge fluctuations are probably also not important, right?
When you say charge fluctuation,
Well, the electron, there's a few electrons in but the elements are neutral, right?
yes, right. When you did that, then it's right. Okay. So the equation of state is, a relationship among these things. It tells you the pressure as a function of graph. I tell you this fluid element has this baryon density, this temperature, this proton fraction. Then the equation of state tells you the pressure, the energy density, all the different things you might want to know. And that's, of course, needed to do a simulation of a merger. You need to know how squishy is the stuff, right? Gravity tries to squish it. Well, how hard do you have to squish it to get it to a certain density? Okay, they do that. That's the part I'm taking for granted. I'm interested in the deviation from equilibrium. So let's start thinking about this particular way of being out of equilibrium that I'm interested in here. And that is what's called beta equilibrium. So each fluid element relaxes to a particular proton fraction. So if you give a density and a temperature, then the fluid element will relax towards a favored proton fraction at that density and temperature. And that is determined by some properties of the strong interaction, the nuclear symmetry energy, and the requirement of electrical neutrality. The electrons and the protons have to balance. So between those things, that determines this favored proton fraction. The weak interaction is the thing that makes it happen. It can turn protons into neutrons, so it can change the proton fraction. So it drives the relaxation of the proton fraction to its favored value. And for a typical equation of state, this is an example of the equation of state based on a relativistic field theory called IUF, fine, at zero temperature. When it equilibrates, this is how the proton fraction looks as a function of density. So for this particular equation of state, at twice saturation density, twice nuclear density, it wants to be about 7% protons, right? 93% neutrons, 7% protons. If you push the density up a bit, it wants to be more like 10% protons, and so on. And so you've got a density-dependent proton fraction that it wants to relax. Everyone okay with that? So you might then ask, what happens when?
If I may ask, I'm a little surprised that the photon fraction goes up with density. With this naive argument that it is sometimes told in the undergraduate level, right, is that with increasing density, then the electrons get pushed into the photons.
Yeah, that's already happened. So that happened long ago, and much lower.
Wouldn't that imply that it should be the other way around?
No, so lower down, at very low densities, that is happening. But once we get to here, as you go to higher and higher densities, the difference between the neutrons and the protons is in some way becoming less important. Okay, as you go to very high density. The protons are highly non-relativistic, and the neutrons are getting to be relativistic. Because the neutron density is higher, so the Fermi density is higher. So the protons are non-relativistic, the neutrons are becoming relativistic, so they behave somewhat differently.
It's driven by the Fermi statistics.
Yeah, well, and yes, Fermi statistics and what's the mass of a neutron or proton compared to what's the Fermi momentum. And we're getting to the point where the Fermi momentum is getting comparable to the mass. Anyway,
Right. Okay. So
it gets into some detail, right? But
so the naive argument goes at much lower.
much lower than that. Yes. Okay, so you've got this density dependent sort of long run. If you leave it long enough, it will settle down at a given density. It will settle down if you leave it long enough with a particular proton fraction. Okay, so this doesn't happen instantaneously, right? That's the whole point. The weak interaction is what turns neutrons into protons and vice versa. And the weak interaction operates on much slower timescales. I don't know if you're familiar with weak interaction processes, but a well-known one is the fact that the neutron becomes unstable if you leave it on its own. It decays in about 10 minutes. Right? That's so, and the muon, right? Muons created in the upper atmosphere by cosmic rays, their lifetime is about a microsecond. So weak interactions vary greatly, but their time scale, microseconds, seconds, much more like the millisecond time scale that we're talking about. Okay. So weak interactions may or may not get you to here quickly. That's going to be the main question here, is how quickly you get to equilibrium. So density oscillations, if I vary the density, like you saw the density oscillations where the density was varying in milliseconds. So if you're varying the density in milliseconds here, the question, you may drive the system away from the ideal proton fraction that it will eventually have in the long run. And this has got different names. People call it chemical equilibration, isospin, because it's neutron proton, beta, because it's beta processes, flavor equilibration. It all mean the same thing. They all mean trying to get back to the right proton fraction. So that's all. There's only one thing going. One. Oh, okay, yeah.
Right.
Well, it means the one that it will settle down to if you leave it long enough. The one that the weak interaction takes if you leave it long enough. The long run static proton fraction. Temporarily, you can drive it away. That's what we're going to talk about. So let's look at a sort of cartoon version of this. We're going to think about a fluid element that undergoes a density oscillation. So here we go, here's an equation, but it's not the world's most complicated one. We imagine some fluid element, its density varies in time. How does it vary? Well, it's got an average density, and then it's got some sinusoidal oscillation in density with amplitude delta n and angular frequency omega. Okay, so that's like one of those little fluid elements. Sweet on sweet, sweet on. And what we also, that's an externally imposed condition. The merger is doing that to this fluid element. And then we're assuming that the proton fraction, this xt, always wants to relax towards its equilibrium value at some rate gamma. So it's a very simple little differential equation here, saying the rate at which the proton fraction changes due to weak interactions is minus this relaxation rate times how far it is away from equilibrium. So when it's in equilibrium, it doesn't want to change anymore. If it's out of equilibrium, it wants to head towards classic, exponential decay towards final state. That makes sense to everybody? Okay, so we got these, basically we've just got two very simple equations here, and we can put them together and solve them and see what sort of behaviors we get. So let's start with, imagine, we've only got two time scales here, right? We've got what's the frequency of the oscillation, and we've got what's the equilibration rate, 1 over the equilibration time. Okay, so we've got 2 time scales. So we can look at basically some simple situations. Firstly, suppose the equilibration is fast compared to the oscillation frequency. So here's a cartoon of that thing I had on the previous slide. Density along here, proton fraction up here. This is the equilibrium value. I've turned it into a straight line to make that simple. So imagine that the equilibration is fast compared to the oscillation timescale. What would you expect? What would you expect the system here to be doing? If I oscillate the density from 1 to 3 times saturation density, where would you expect the system to go on this plot if the equilibration rate is fast? Suggestions? It would be above, so it would have a higher proton fraction than it will in the long run. Do you think it should stay on the line? Who thinks it should stay on the line? Yes, right. The equilibration is fast, so that means it always stays in equilibrium. On the time scale on which I'm oscillating it, it's quickly equilibrated. So I squeeze it a bit, equilibrates. Squeeze it a bit more, equilibrates, right? It's fast, it's quick to equilibrate. So it stays in equilibrium the whole time. So what you see is something like this. If I'm oscillating, or 2 to 4, twice to 4 times. So if I'm oscillating the density back and forth, it's always staying pretty close to the line. Okay, so that's what happens if I solve these 2 equations and I make gamma, this relaxation rate, be much faster than omega, the oscillation frequency, then it goes back and forth along this line. And that means the proton fraction always stays equilibrated. So basically, I don't even need to solve the relaxation equation. I can just say the proton fraction will always be what the equilibrium condition says it should be. I can drop this equation from the number. Right? I always know. Tell me the density. I know the proton fraction. I don't need any damn equation. Well, let's think about what am I going to suggest we think about next? The opposite limit. Very good. Very clever grad student there. Okay. So how about slow equilibration? Supposing the relaxation rate is very slow compared to the frequency at which I'm oscillating this fluid. Now, what sort of shape is the system going to describe in this plane as I oscillate the density back and forth? Somebody not in the front row. I love the front row. What do you think it's going to go vertically? So the density isn't actually going to change. It's going to stay at the same density the whole time. A triangle way, but it's got to go in some sort of periodic shape, right? It's got to come back to itself. This periodic oscillation. And what you think it's going to go where? Horizontally. Horizontally. What do you read with that? Why are you saying that?
The total fraction, the integration for the fractions of the with the binary density, because that is that definition of equilibrium. Response rate is so low, physically doesn't have information.
Right. So that is correct. So let's go on and show that. Okay. Here we go. So what's happening in this case is the system never relaxes, and that means its proton fraction never changes. If it's 10% protons, and I squeeze it a bit, it's still 10% protons, right? Then the protons and the neutrons are in a smaller volume now, but none of the protons have turned into neutrons. None of the neutrons have turned into protons, because the processes that do that are really slow, and they haven't done anything yet. So it stays at the same proton fraction the whole time. Okay? Because the number of neutrons and number of protons is both conserved. So I squeeze it by a factor of 2, the densities both go up by a factor of 2. Nobody changes their identity. So that's what happens if the equilibration is slow. And again, I don't need to solve the relaxation equation. The proton fraction is just determined by history. Like, what did we start off with? Proton fraction of whatever it was, 6%. Well, the relaxation processes aren't doing anything, they're too slow, so it just stays at 6% the whole time. I squeeze it, I unsqueeze it, I squeeze it, I unsqueeze it. Proton fraction is fixed. No need to solve this equation. So what I'm saying here is if these, in either of these two conditions, the people running the merger simulations don't need to include this equation in their dynamics. Right? They don't need to do anything beyond what they're already doing. They can either treat proton fractions frozen, or they can treat it as always in equilibrium. Okay, they've got two simple rules, one or the other. They just follow that rule, and they don't need to include any sort of out of equilibrium or relaxation dynamics, i.e. equation, in their merger. What am I going to ask you about now? This is critical endpoint, critical equilibration, you can call it different things. What happens if the relaxation rate is the same as the oscillation frequency? Now what happens? Any idea? You'll suddenly be shy. What do you want to wave their finger in the air and show me a shape? Sine wave. Well, so sine wave. How you mean sort of it goes off and
Yeah, if it's if the relaxation rate is equal, so as it increases the proton fraction also
right,
goes to equilibrium, then it decreases and it again increases.
right. But so what shape is it going to describe in this plane here? It's not, it can't quite be a sine wave, because the sine wave goes on forever in some direction. Right? So it is kind of a sine. So wave your finger more.
Stop.
Everyone look at her finger. Oh, you're doing great. Your finger is doing physics. I've done what you were doing before. Okay, I salute you for your willingness to participate. So it's kind of a Lissajous figure, if you those things. So you compress, you increase the density, the proton fraction goes up. You decrease the density, the proton fraction goes down, but not along the same track as it went up. Right? It's got memory. This is sometimes called histories. Okay, it's got a sort of memory that gets compressed, and then it turns around and uncompresses again, but it still remembers that it was recently compressed. So if you solve those equations, you get this sort of shape here. So this is interesting. Okay, what this means in this situation, the proton fraction doesn't just depend on what's the density right now. If the density right now is 3 times saturation density, what's the proton fraction? I don't know. It depends on what was going on a millisecond ago or 2 milliseconds ago. Right? Depends on the recent history. Now you need to include that relaxation equation in your fluid dynamics in order to get a correct account of the behavior of this fluid dynamics. So that's my method. So in a sense, this whole talk I'm giving you is sort of like my pitch to the merger simulation people about do they, and if so, when do they need to include this extra equation in their simulation? And of course, that's unwelcome news, right? They don't want to make that. It's already complicated doing dynamic GR. So non-linear general relativity. It's already complicated. They don't want to have an equation quite reasonably, and so they need very good reasons if they're going to include more equations in their simulations. I'm showing you how does one make the case that an extra equation is, which I haven't made yet. I've just showed you that there are circumstances where it might be needed. What are those circumstances? They are where the typical density oscillation frequencies, which the merger people already know in the Taylor range, are equal to the relaxation rate. So the question would be, are there situations where this comes up? Are there situations where the relaxation rate of the proton fraction is indeed in the kind of kilohertz 1 millisecond range? And if there is, this extra relaxation equation is going to be part of the dynamic. And it turns out that when you have this critical equilibration, this leads to some interesting things. Phase lag, bulk viscosity, damping density. I mean, I get to it in time, but guidance, yeah, it's a thing, and I'm not going to get to it. But you know, so is there critical equilibration in mergers? Let's see where I do get to. So this now you have to start doing a so we know the frequency, it's about kilohertz. What's the relaxation rate? Now you have to start doing calculations. You have to do calculations of how fast are those processes, those ERCOT processes in Doctors of Rio de Janeiro. How fast are they in nuclear matter of twice saturation density and temperature of 10 MeV or 5 MeV, whatever it might be? That's the situation. Right? We want to know, does it ever come out to be like a kilohertz? So the processes you're looking at depends whether it's neutrino transparent or neutrino trapped. There are things like neutron decay into a proton and an electron and an antineutrino, or proton eats an electron and turns into a neutron, or if it's neutrino trapped, you can have processes with neutrinos in the fission state. But this question is still the same. Calculate the rates of these processes and ask, is the relaxation rate for the proton fraction ever comparable to the density oscillation timescale? So I think I'm luckily I just go straight to the answer. It's very good timing. So this is the outcome of some calculations done by people, including me. And this is neutrino transparent matter, and this is neutrino trapped matter. And it's on the same axes as we looked at before. Baryon density increasing here, temperature increasing there. So these are the typical baryon densities and temperatures that you get in mergers. And in neutrino trapped matter, you see this relaxation. These are contours. Okay, you see the relaxation rate is very fast, a thousandth or a millionth of a millisecond. Okay, so if the matter has neutrinos trapped in it, then relaxation is going to be very fast, and you really don't need to worry too much about it unless you're tracking things on very short time. If the matter is neutrino transparent, then on these relevant densities and temperatures, you see the contours include a tenth of 100 milliseconds, a millisecond, 0.1 milliseconds, 0.0, and this thick line here is telling you where it agrees with 1/3. So indeed, there are conditions in neutron star mergers if the matter is neutrino transparent. Under neutron star merger conditions, these densities and temperatures, you do indeed get this critical equilibration, this resonance between the relaxation of the proton fraction and the applied density oscillation. And it's sort of an amazing coincidence because that applied density oscillation, as your question highlighted, has to do with some sort of strong interaction stuff, the speed of sound and the size of the object. The weak interaction relaxation rate has to do with very different things, right? The Fermi constant or the mass of the W or however you want to describe it. These very different pieces of physics. There's no real reason they should have anything to do with each other. So, okay. Yeah, so the thick contour shows critical equilibration. All right. So, yeah, for different equations, the state still looks about the same. So that's that. I think I'm going to need to jump ahead quite radically here. Yeah, oh, so good. So we have conclusions so far, and then we can just not do part 2. So great. Okay, so the conclusions so far are that in neutrino trapped matter, the proton fraction relaxes quickly. In neutrino transparent matter, it can relax on the same time scale, so you'd want to include the proton fraction equilibration in the dynamics. Now, so the neutrinos this makes it clear that neutrinos are a key player. So the question would be, are neutrinos trapped or escaping? And that's a question of what's the neutrino mean free path, right? The mean free path is about the size of the star, 10 kilometers or so. Neutrinos will escape like radiation, and indeed it will be neutrino transparent. If neutrinos have a mean free path of a centimeter, 30 kilometer size object, then they're going to be trapped. They're going to form their own equilibrated gas, and then it's going to be like this. So which is it? Well, because neutrinos are weakly interacting, it turns out that depending on density and temperature, they sort of transition between these two regimes. At the lower temperatures, like less than an MeV, their mean free path is very long and they escape. At the higher temperatures, tens of MeV, they are trapped. So they're right in this inconvenient regime where they're not actually either of these. I use these two things as examples because they're simple situations where you can you know how to treat the neutrinos and you can get a simple answer. But the unfortunate truth about neutron star mergers is they have highly non-trivial neutrino transport going on, with the neutrino mean free path being comparable to the size of the system, which is a nightmare. So unfortunately, there isn't a clear answer to which of these two regimes were. So the bit of the talk that I'm not giving you was to do with if you have critical equilibration, are there physical consequences? And that's where I would talk about bulk viscosity and things like that. But I will jump through all those slides and get to my very, very concluding slide. So you will get to see all sorts of exciting things that you'll have to invite me back again.
Sure, we do that.
It's a very clever scheme I have here. Okay. So the summary is neutron star mergers probe the dynamical response of dense matter in the millisecond timescale, and we already saw that in neutrino transparent matter you get critical equilibration, and so that leads to bulk viscosity, which dampens the density oscillations in an interesting timescale, 20 milliseconds. So it could actually affect those oscillations. And then if we ask what's the sort of next things to do, there's all sorts of next things to do. You could try and look beyond, like I said, it's not really transparent neutrinos, it's not really trapped. We could try and look at arbitrary neutrino distributions, which are what would ideally you would get in emergent simulation to trap neutrinos accurately, but trap them and have some arbitrary distribution, not a nice thermalized Fermi Dirac. And so you can look at that. You can go beyond neutron, proton, electron matter. You can look at other forms of matter, hyperonic matter with lambda and sigma, baryon, and stuff like that. Some people have looked at that, including my postdoc, and it seems like the relaxation is going to be fast in those forms of matter. You can look at other phases, pion condensed matter, nuclear pasta, for those who know what that is. If you don't, it's a tasty treat for the future. Quark matter. Okay, I talked about bulk viscous damping, flavor equilibration. You can also look at other manifestations of flavor equilibration. Yes, it damps oscillations, but it can also lead to heating. It can also lead to its own source of neutrino creation. So those would be interesting things to look at. You can not look at flavor equilibration. You can look at thermal conductivity, temperature equilibration, shear viscosity, shear flow equilibration, which seem like they can become significant in the neutrino track regime. And then you can finally look beyond standard model physics. This is all standard model physics. You can look beyond standard model physics. So I cheated. I do actually have one more slide. And that is that my grad student, Stephen Harris, looked at axion-like particles. So cooling by axion emission. And so here is temperature along the bottom and the axion coupling, the strength of the axion coupling up the side here. And he's looking at how long it would take for a hot region to cool to half its original temperature by emitting these hypothetical axion particles. So if it happens quickly enough on millisecond time scales, it'll affect the merger. If it happens on long time scales, it doesn't affect it. So what he found, in his collaborators here, was that at the highest temperatures here, and this is super 1987A limit that says really the axion coupling should be less than that, otherwise it would have messed up the supernova that we've observed. So the sort of physically believable part of this is at the bottom here. So if the axion coupling is the strongest that's allowed by that limit, and the temperature is at the upper end of the temperatures that we see in simulations, then indeed you see a 10 millisecond cooling time here. Emission of axions could cool a fluid element quickly enough to be relevant to the dynamics of the merger. So you can even look at constraints on beyond the standard model physics in this dynamic situation of a neutron star merger. So okay, I will retreat from that cheating extra slide, and thank you very much for listening.
Okay, thank you so much for the very interesting talk. So do you have any questions? Maybe we give priority to the graduate students first, if they have any questions. Please.
You showed a plot, I think, on slide 10 about how the temperature changes when it merges and it.
You want me to go back to that slide? Oh, ask your question, I'll judge. Yes. So to do a neutron star merger simulation, you have to have an equation state. So they assume some equation state, they assume some initial masses of the two neutron stars. I don't know if those have spin or not, but if they did, they have to assume some orientation of the spins and some spin frequency. So yeah, there's a bunch of initial conditions, and there's an assumption about the equation state. and they neglected any form of relaxation, transport, anything like that. So no thermal transport, no flavor relaxation, no shear flow, no shear viscosity, numerical viscosity. So yes, but it's a guide, right? It gets you a rough idea of what's probably going on.
Where on the gravitational wave signal is basically anything that frequency
Right, so the density oscillations that are going on inside the star don't directly show up in the gravitational wave signature. The gravitational waves are created by large-scale mass movement. So it's the fact that you've got something that isn't spherical spinning around. It's two blobs that are emerging, and they're going around each other. So that's a non-spherical situation with a quadrupole moment. And that big, gross, 10-kilometer scale mass distribution, that's what's emitting the gravitational waves. These little density oscillations bouncing back and forth inside it, sort of, oscillations in there, but they're not directly emitting gravitational waves. So what sort of imprint they might have on the gravitational waves is very hard to say. That's why you need the merger simulation. It's very difficult to have an intuition of changing microscopic parameters or phenomena and asking how would those translate into something at the end, because the whole thing is so nonlinear. That's why we're doing a simulation. Right? So you just have to kind of try it with different parameters for those and see what comes out. It's a bit of a black box.
Okay, let's have a final question.
I'm just wondering, what is the Detroit wavelength of the neutrino, and how would it compare to the Neutron has? Is there, in other words, is there interference with the input and process of escape?
Right. So the temperature, the critical energies are in the MeV range. Okay, and the mean-free path is typically in the sort of centimeters, meters, kilometers range. So they're very different, right? MeV would be 1030. So for the most part, I think always for our purposes, there is that clear separation to scale.
Okay. Okay, the final
So a glitch is a thing that happens in an isolated neutron star that's settled down as a crust. And then there's at some point there's a redistribution of angular momentum in the star between the inner part and the crust, which is hypothesized to be happening through superfluid vortices that thread up through the middle and then attach to the crust, and then they break and relocate. That's the current scenario of the glitch. So it is quite different from what's happening in emergence.
Okay, let's differ further questions after the seminar. So thank you very much again.